If you're like me and am curious about the power consumption or energy usage of various appliances throughout your house, then this is the project or product for you. This here is a home power and energy monitor, which utilizes an Arduino R4 as the brain power and is able to connect to the Arduino Cloud, through which is able to display power and energy consumption information to you very quickly and very easily. So in this video, we're going to take a quick look at how this works both from a hardware perspective and a software perspective, and show a demonstration of it in action to see what this thing can do. And just a disclaimer before we get started that this project does involve the use of mains high voltage. Therefore, do not try this at home unless you are trained or qualified to do so. So first, let's take a look at the external features of the project. So this box here is 3D printed PLA plastic and measures about 20 centimeters by 20 centimeters by 7.5 centimeters tall, which is a good size to be able to fit, say, on a kitchen counter with various kitchen appliances, or to be able to fit somewhere easily for storage if not in use. On the front here, we have two AC outlets, which are the input to the system. These outlets are what the appliances we wish to measure are plugged directly into, so that their power and energy usages can then be measured by the system. On the top of the box here, there are just a couple of simple slits, and those slits have two main purposes. One is to help with overall ventilation and airflow through the system, and the second is to better help the Arduino inside connect to the Arduino Cloud and the dashboard through which it displays its data. And one of these slits can also be seen here on the side of the box, again, just to help with overall ventilation and connectivity. And lastly, on the back, we can see that there are two main features here. So first is the output, which consists of two AC cables. These get plugged into kitchen wall sockets simply because those sockets are oftentimes wired where the top socket is on one phase and the bottom socket is on the other phase. So not only are we able to measure the power and energy of simple kitchen appliances, but we're also able to get a better idea of power usage per phase in the home overall. And as well, on the back of the box, there is a small label that says power. That is to notify the user which of these two cables will lead to powering the Arduino directly. So therefore, if you're only measuring one appliance rather than two, it's important to plug that power cable in so that the Arduino itself actually gets power and is able to operate successfully. That'll all be seen now when we open up the box and take a look at the inner electronics and the hardware connectivity of the system. All right, so opening up the box, we can see now the inner electronic components that make the entire system run. So from our input outlets on the front, we have two wires from each outlet. The white represents the neutral, and the black wire represents the live wire. And as I said at the beginning of the video, this is high voltage AC and can be lethal if you're not careful, so please do not try this at home. These wires then go one directly to the one of the outputs, and the other one goes into a box which also consists a third outlet. So this internal outlet is wired both by one of the outputs and through one of the inputs, and connects to a 12-volt DC power adapter, which is used then to power the Arduino internally inside the box. So these live wires, represented by the black wires here, pass through current sensors. These sensors are the ZMCT103C sensors, which use a current transformer, these big blue components right on the back, which use the magnetic field of the current passing through the wire to read the current which is passing through from our appliances to the wall itself. So the output of these current transformers or current sensors are 1 volt per every 5 amp input. While that is the ratio, these current sensors can handle up to an absolute maximum of 10 amps, though that would be the absolute maximum of the system. So if we're assuming a 120 volt AC voltage and a maximum of 10 amps, we are limiting the project to about 1200 watt appliances, which for the vast majority of time, most kitchen appliances will never draw near that much power from the grid. So this should be a reliable system for the vast majority of appliances. But it's important to get an idea of where the maximum lies so that there is no damage done to the internal workings. So the output of these current sensors are then passed to the Arduino R4 through its analog inputs. It reads that output voltage, and based on the calibration that was worked into the code, it's able to accurately calculate the current read by the sensors and then able to multiply that by the voltage in order to get power. And it's also able to calculate the energy through which it then uses the Arduino Cloud to display that information to the user. So in order to get a better idea of how all of that actually works, we're going to take a quick look through the code for the project and how the Arduino is actually able to calculate those values and utilize the Arduino Cloud to be able to display them to the end user. To look at, now that we've looked at the hardware, is to look at the software, or how the Arduino itself is actually able to take the readings from the sensors and calculate power and energy, and then display it to the Arduino Cloud, which we'll see in a demonstration shortly in the video. So to get started, we're just including the thing properties, which is defined by the Arduino Cloud itself, and that sets all the cloud variables through which we are able to display on the dashboard. Next, we're going to look at a few other predefined variables created for the project. So there's a constant voltage of 120 volts, and that there is just assuming that we're operating in, say, North America, where our outlets use 120 volt AC and not 220 or 240. Then we have a fair number of current variables, including the standard current for each phase. Those are read directly from the sensors. We have peak current variables, which is the maximum current in a given time frame of readings. The RMS current, or root mean square current, for each phase. That will be important for actually calculating the power. And finally, a variable for counting milliseconds, which is used in a small timer later on in the code, which we'll take a look at. So now going to the setup loop of or setup function of the code. So we're starting the serial monitor with serial.begin, running a command called analog read resolution. That is changing the resolution of the internal analog to digital converter in the Arduino from its standard 10 bits to 12 bits. That just adds a bit more accuracy into the readings from the sensors. A small delay is then called just to make sure everything's set up correctly. And then these are predefined functions from Arduino Cloud, which sets all of the variables in the cloud, begins connecting to the cloud, and then runs some debugging information as well, and prepares the system to be set up and start receiving data from the Arduino. And that is when we enter the loop function of the code and start actually reading the data from the sensor and displaying the power and energy on the dashboard in the cloud. So taking a look through the code here, the first line is just to update the cloud, to send a quick update from the Arduino to the cloud with new variables that were calculated throughout the loop. And then we have a few commands that are acting almost as a timer to get how many milliseconds have passed since the previous loop. And this is important to calculate the energy of the overall system, as energy is the power usage over a given time. So we're calling a millis function and then getting a differential between the current amount of milliseconds that we have been running the entire program, subtracting from this variable called previous milliseconds. So for example, if the system has been up to this point running for 800 milliseconds and the last loop and it's only been 50 milliseconds since the last loop, then our previous mills would be 750 and current mills would be 800. So our differential would be that 50 milliseconds. Then we are resetting our peak current values to 0. And then what we're doing in this for loop is reading the current values over 600 cycles in order to actually get a peak current value. So here we are reading a for loop for 600 cycles, reading the both of the sensors, and then calculating new peak values for both current A and current B, or from sensor A and sensor B. And then coming down here, these are two if statements that act as calibration for the system. So when the Arduino is first powered on, the sensors do output a certain value, standard. So these were measured and then accounted for. So sensor A was reading 1900 upon no load, and then sensor B was reading 1800 upon no load. So if we subtract those off, and if the sensor is reading anything at that value or less, then we're going to say that the sensor is off and that nothing is connected and there are no devices being measured. And finally, the last bit of the code is to actually calculate the power and energy. So the RMS current is calculated through this factor of 5 amps per 1 volt of the actual sensors, the resolution, 12-bit resolution, and then multiplied by the square root of 2 to get our RMS values. And then our power is our RMS current multiplied by our voltage, which 120 volts is already in RMS. And then our energy is the collective sum of our power multiplied by our time in milliseconds, which is then converted into hours to be able to get our unit of watt hours, which is displayed on the dashboard. And then as well, we are calculating our total power and our total energy, which is also then displayed on the dashboard. Running a quick delay, and then the cycle goes all the way back. The Arduino updates, the cloud gets new variables, and the cycle continues so long as the Arduino is running. So now that the code's explained, we're going to go ahead and do a quick demonstration and see the entire project in action and see how all of these components come and fit together to create one final working project. So to conclude, I'm just going to finish the video off by giving a quick demonstration of the final working product, and to bring everything that we brought up in the video together to show how every component works to create the final project. So it's already plugged in to the wall just to give the Arduino some time to connect to the Arduino Cloud. And we're going to be measuring two common kitchen devices, one of which is a toaster and the other is a kettle, which are both pretty common appliances used every day, for example, for making breakfast. So coming over to the dashboard, as we can see right now, everything is reading 0. This is expected as both of the appliances are currently off and are therefore not drawing any current from the grid. So come over and first of all, pop the toaster down. Just one for now, and come back to the dashboard. We can see that everything is updating. So we have the power of phase A, the energy, and as well the graphs of total power and total energy are beginning to adjust and change to account for this new data. Phase B is currently still off as we have the kettle still off. However, if I come over and I flick this on, then we can see that, boom, phase B is also coming alive. So not only is it also reading a power draw and energy consumption, but the total power and total energy has shot up as it is now taking this new phase into account. So if I unplug the kettle or turn off the kettle, then that power will drop back to 0, but the energy will remain constant now, as that has been the energy usage over the time of which we're using the kettle. And the toaster will keep going until the toast pops or whenever that's finished, but as of right now, that's still reading its values. So to conclude, the project does work successfully as intended. Thank you so much for watching the video, and of course, stay safe if working on any electronic projects, particularly any involving high voltage such as this one. But again, thank you very much for watching. This has been a very fun and exciting project to work on, and I look forward to doing something more like this in the future.